This is my Precalculus course. Today we're going to continue to learn rational functions and how to graph them. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. So we talked about the definition of rational functions in the previous class, and you already saw most of this information. In the previous class, we learned how to graph and analyze rational functions that were in proper form. Well, today we're going to analyze and graph rational functions that are in improper form. So improper form is when the degree of the polynomial in the numerator is greater than the degree of the polynomial in the denominator. But improper form is also when the degree of the polynomial in the numerator is equal to the degree of the polynomial in the denominator. Now, when we have a rational function that's in improper form, it's necessary to use long division to change the form of the expression. So here we have a rational function, and you can see that it's in improper form because the degree in the numerator, which is 4, is greater than the degree in the denominator. The degree of the polynomial in the denominator is 2. So what we do is we convert to this expression here, and that will help us to understand what's going on with the graph. And this expression here is what I call an asymptote curve. Even though asymptotes are really supposed to be lines, the graph approaches this curve, this invisible curve on the graph. And we're going to talk more about that later. But as x gets really, really big in the positive direction or the negative direction, this expression here will approach 0 because the degree in the denominator is, well, we'll say it this way: the degree in the numerator is less than the degree in the denominator. So you have to keep dividing until you get a fraction that fits that description. You don't want this situation where the degree is greater in the numerator. You want your leftover fraction here to be in proper form. So that's why we say we're converting to proper form. But it's not really that great of a description of what we're really doing, because we're taking a fraction and we're converting it to this form, whatever you want to call it. But as x gets really big, this expression approaches 0, which means that as x gets really big, this expression really becomes irrelevant, because the graph starts to look like this expression, which means, again, this represents an asymptote that is curved. And of course, you know how to use long division in order to convert. We take the numerator and we divide it by the denominator, and we get this expression down here, which helps us to graph. So I want you to get a picture of all this information and get a picture of this information here. Most of this information you've already seen, but we just have that extra part here that you have not seen. So again, in the previous class, we dealt with situation number 1, where we found the vertical asymptotes, and we also dealt with situation number 2. But we did not deal with this situation down here, where our rational function is in improper form. In that situation, there's probably going to be a horizontal asymptote, but it's not necessarily going to be on the x-axis. Also, we might have an oblique asymptote, and like I said, we might have a curved asymptote, but I didn't put that in the description here because technically asymptotes are supposed to be lines. So let's begin. We're going to start with situations where the degree of the polynomial in the numerator is equal to the degree of the polynomial in the denominator. So the degree here is 1, and the degree here is 1. So they're equal. But that's still considered to be improper form. So the first thing we'll do, we can find the vertical asymptotes first. That's going to be pretty easy. We know that this is not a whole because there's no common factors in the numerator, and we don't have a common factor in the numerator and the denominator, so we know x equals 2 is a vertical asymptote, and we can go ahead and graph that. And so now we want to find the horizontal asymptotes, but we can't really do that without using long division. Now, in my calculus course, I'm going to show you a faster way to do this, but for now we need to practice our long division. So we're going to take the numerator and divide by the denominator. So x times what is equal to 4x? X times what is equal to 4x? Well, obviously that's going to be 4. And then we need to, that's step number 1 of long division. Then we need to go on to step number 2, which is multiplying that number by the divisor, and we get 4x minus 8. And then we're going to subtract. These obviously cancel out, and negative 5 minus negative 8 is 3. Okay, so we can stop there because the degree of the remainder is less than the degree of the divisor. The degree here is just 0 because that's the same thing as x to the 0, 3x to the 0. So we're done. Now all we have to do is write the new form. So f of x can be written as 4 plus the remainder divided by the divisor. So we change the form of this to this, and you might say to yourself, who cares? Why did we do that? What was the point? Well, now look what happens as x gets really, really big. As x gets really, really big, this fraction approaches 0. Now how do we know that? Well, because the numerator is not changing. As x gets really, really big in the positive or negative direction, that doesn't affect the numerator. The numerator is always going to be 3. But as x gets really, really big, the denominator increases. And so you might have 3 divided by a trillion. Well, a 3 divided by a trillion is a small number. It's so small that you can just consider it to be 0. So as x gets really big, this fraction just disappears, basically. It approaches 0. So what you're left with is 4. So what this means in terms of the graph is that as x gets really, really big, the graph approaches this horizontal line 4. So we can say, because this fraction is in proper form, and we know that this fraction approaches 0, we can say that the horizontal asymptote is y is equal to 4. And I guess I'll just rectangle these because those are part of the answers. So now we're going to draw the horizontal asymptote. And I'm going to make that a little bigger. So we have a horizontal invisible line at y equals 4. Okay, so now let's find the y-intercept. So obviously to find the y-intercept, we let x equal 0. So we plug in 0 to the function. And we get 5/2. So the y-intercept is 0, 5/2. Okay. So that would be roughly here. And now let's find the x-intercept. So for the y-intercept, we let x equal 0. For the x-intercept, we're going to let y equal 0. So we have 4x minus 5 over x minus 2 is equal to 0. We want to know what x value would make this fraction equal to 0. We want to solve that equation. Well, remember, in order for a fraction to be 0, the numerator has to be 0. And technically the denominator has to not be 0. So we want to figure out what makes the numerator 0. So we're going to set that equal to 0 and solve, and we get x is equal to 5 over 4. So the x-intercept is 5 over 4, comma 0. Or we can change that to a mixed number. We can say 1 1/4, comma 0. Okay. So we have that point there. So now we're ready to graph. Well, actually, let's do our sign chart. We can probably graph without the sign chart because we have a pretty good idea of what it's going to look like, but let's use our vertical asymptote and our x-intercept to help us graph. So I'm going to plug in 0 to the function, and we already did that. We got positive 5/2. So let me find a pen. So here we have the graph above the x-axis, and now let's plug in maybe 1.5 here. If you plug in 1.5, we just want to see what the sign is going to be. We don't really care about what the number is. And so it looks like we get a negative number. And let's plug in 3 up here. If we plug in 3, we definitely get a positive number. Okay. So what this tells us is that in this region, our graph is going to be below the x-axis. And in this region, our graph is going to be above the x-axis. And in this region, our graph is also going to be above the x-axis. Okay, let's connect the dots. Alright, and I'm going to try to make that a little thicker. And let's find another point up here. So let's plug in maybe 3 into our graph. So it's actually might be easier to use this expression. We get 7. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. So it's just barely on the graph. Let's try plugging in maybe 5. If we plug in 5, we get 5. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And then we can just connect the dots, and there you have it. So that is the graph. We don't have any holes because we don't have any common factors in the numerator and the denominator. So that's it. That's how you graph a rational function that is in improper form when the degree of the numerator and denominator are the same. We have to use long division to see where the horizontal asymptote would be. Let's try another one of these problems. So let's start with the vertical asymptote. Now in this case, we can't really see if there's going to be any holes in the graph, so we need to factor. And you may not always be able to factor the quadratics, but that would make the problems much more difficult and tedious, so I'm not going to make you use the quadratic formula to find how to factor these quadratics. So let's write this up here so we have more room, and we're going to continue to factor. And we have x minus 4 times x plus 2. And you can see that we don't really have any holes in this graph. So we don't have to worry about that. But we do have vertical asymptotes at 4 and -2. So just to be clear, I got those equations from these factors here. I'm going to bring this label up here. We can also see the x-intercepts. That's these green factors up here tell us what the x-intercepts are. So we see we have -5 and -1 because that makes the numerator of the fraction 0. In order to find the x-intercepts, we have to set the function equal to 0, and the function is this big expression up here. We'd prefer to have it in factored form because we can see the x-intercepts just by looking at that graph. We want the y value to be 0, and if the y value is 0, then we see that x is going to be equal to -5, or it's going to be equal to -1. Now to find the y-intercept, we just find f of 0. We plug in 0 for x. And then we get 0 plus 5. We can use the factored form if we want. It doesn't really matter which form you use, whatever's easier. We plug in and we get 5 over -8, or double -8, which becomes +8. So we have the point 0.58. That's the y-intercept. And we have the x-intercepts -1, 0, and -5, 0. Okay, so now we're going to find the horizontal asymptotes. So I'm going to divide the numerator by the denominator. This is just the easiest way to find an expression. It will show us the position of the horizontal asymptote, if there is one. And let's do the math. And we get the following. And that's it. So now we're ready to write f of x in a slightly different form. Maybe I'll put this up here. So f of x in our new form is now -1 plus 8x plus 13 over negative x squared plus 2x plus 8. So all we did was simply change the form of this blue expression up here. We changed it to this. And now we can see where the horizontal asymptote is. Because as x gets really big, if x is a really, really big positive number or a really, really big negative number, then what happens is this fraction disappears. Or it approaches 0 more precisely. And for really big x values, you can just consider that fraction to be 0 in your mind, which means that the y values are going to approach -1. So that tells us what the horizontal asymptote is. So we can write that down here. We can just say y is equal to -1. And on our rectangle, technically we're not really looking for these numbers as answers, but I'm just going to rectangle those, showing that we found that information. So now let's draw our x-intercepts. -1, -5, and we have a y-intercept at 5/8. And we have vertical asymptotes at 4 and -2. So I'm going to mark those on our sign chart. And the x-intercepts -1 and -5. The spacing on your sign chart doesn't really have to be perfect. So it's really not that important. It's just to keep track of the sign of the y values in certain intervals. Okay, so let's plug in a value for the region at the far left. Let's plug in -6. So plug in -6 to the original expression there, and you can see that it's not going to be easy. So it'd probably be best to plug in -6 into this expression up here. So -6 plus 5 is -1. -1 times -6 plus 1 is -5. So the numerator becomes 5, and the denominator is going to be -6 minus 4 is -10, and -10 times -6 plus 2, which is -4. So we have 5 over 40, and then don't forget this negative out here. So that would be -5 over 40, which is -1/8. So we get a negative number there. And let's count out 1, 2, 3, 4, 5, 6, and down 1/8. So we can go and mark that point as long as we found it. If we plug in -3, we get a positive number. And if we plug in -1.5, we get a positive times a negative. Divided by a negative times a positive. So that results in a negative number. You don't really have to find the numbers, you can just use signs. So now we're going to plug in 0, and we actually already did that. We got positive 5/8. So that region is going to be positive. Now let's try plugging in 5. We plug in 5, we get a positive times a positive. And on the bottom we get a negative times a positive times a positive. So that's going to give us a negative number, negative y value. So now that we have our sign chart, we can start to connect some dots. Let's try plugging in 1. And we have our function down here, so we can plug in 1. We get 6 times 2 is 12, divided by negative 3 times 3, so we get 12 over 9, which is 1 1/3. So we plugged in 1 and got 1 1/3. That kind of tells us where the graph is going. Our graph is obviously going to approach the asymptote there. Now it looks like this graph is going to do something like this, but let's get some more points. Let's plug in negative 3. If we plug in negative 3, we'll get 2 times negative 2 over negative 7 times negative 1, so that's going to be negative 4 over negative 7, which is 4/7. So it'll be about there. Draw that. Remember, we found our horizontal asymptote at y equals negative 1. And so as the graph goes to the left, it's going to approach that asymptote. So again, the asymptotes kind of serve as a guide. So let's try plugging in 2 to our function over here. So we get 7 times 3 over 2 times 4. And we get 21 over 8. And you can use your calculator if you want to make things easier. So if we go out 2, we go up 12.6 roughly. And we can connect the dots. And let's find one more point. Let's plug in 1, 2, 3, x equals 3. And we get 8 times 4 over 1 times 5. So 32 over 5, which is 6.4. So 1, 2, 3, 4, 5, 6.4. So now let's plug in values over here. We know that our y values are going to be below the x-axis. Let's try plugging in 1, 2, 3, 4, 5. If we do that, we get 10 times 6 over negative 1 times 7, so 60 over negative 7. That's negative 8.57. So 1, 2, 3, 4, 5, 6, 7, 8, and that's outside the window. So we can't really graph that point. Let's try plugging in 1, 2, 3, 4, 5, 6. Then we get 11 times 7 over -2 times 8. That's 77 over -16. And that's going to be -4.8. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4.8, roughly. So the graph looks something like this. We don't have to be any more accurate. So as the graph goes farther and farther to the right, it's going to approach that horizontal asymptote. So it's kind of tedious to have to do all that, but you've got to do it anyway. We're not going to do a lot of these problems in this course, so don't worry about it. So what is different about these problems compared to the previous class? The difference is the horizontal asymptotes are not on the x-axis. That's the difference between the previous classes. So I want you to take a picture of everything that we did here, and you can use that to do problem number 3. If you haven't gotten a screenshot of all this information, go ahead and take a screenshot or a picture with your phone. Try number 3. When you come back, we'll do it together. Alright, we're back. So we can see that there's a vertical asymptote at x equals 1, or -1. So let's go ahead and graph that vertical asymptote. And if we let x equal 0, we can see the y-intercept. And it is 0, 1. To find the x-intercept, we let the y value be 0 and then solve. And the only way to make that fraction 0 is to make the numerator 0, and only the numerator. If both the numerator and the denominator are 0, then that means you have a whole. So if we solve, we get 1/3. So the x-intercept is 1/3, 0. Okay. So we found the y-intercept, the x-intercept, and let's graph the x-intercept. It's going to be about there, roughly. And the y-intercept is about there. Those purple points. And now let's find the equation of the horizontal asymptote. In order to do that, we're going to divide the numerator of the fraction by the denominator. And that shows us how to write the fraction in proper form. So we have -3 plus 4 over x plus 1. So this is just a different form of the expression that we were given. So this shows us what the horizontal asymptote is going to be, or where it's going to be located, because as x becomes really big, this fraction becomes really small. And all the y values approach -3, which means that there's an asymptote at x equals -3. Okay, so now we can draw a sign chart. And so let's plug in -2. If you plug in -2, we get a negative number, -7. And we can actually plot that. That goes down here. 1, 2, 1, 2, 3, 4, 5, 6, 7. And let's plug in 0 to test this region here. And we get a positive number, +1. We already have that number, or that point graphed. Let's plug in +1 to test this region. And then we get a negative number, -1. And so let's find some other points. Let's plug in 2. And then we get -1 2/3, and that gives us pretty much everything we need to graph this function. Actually, we should probably find some other points over here. Let's plug in -3 for x. Then we get -5 for y. And let's try plugging in -5 for x. And then we get -4 for y. And that gives us enough to connect the dots. So if you got that one right, excellent. I know that this is tedious, but again, we're not going to have that many of these problems. Okay, go ahead and try number 4, and when you come back, we'll do it together. Okay, we're back. So we want to figure out where the vertical asymptotes are, but we can't really do that unless we understand where the holes are also, if there are some holes. If there are some holes, then we may not be able to differentiate between the vertical asymptotes, so let's factor first. I'm going to factor the numerator, and looks like I factored correctly. And I'm going to factor the denominator. That looks correct. So now we can see that there's vertical asymptotes at x equals -3 and x equals +1. Let's go ahead and graph those. -3 and +1. And when x is 0, we can just plug that in there. So 2 times 0 squared minus 3 times 0 minus 2 over 0 squared plus 2 times 0 minus 3, and we get +2/3. So the y-intercept is 0, 2/3. So let's plot that point. Now let's find the x-intercepts. We can see the x-intercepts by looking at the factored form. to find the x-intercepts, we have to let the y value of the function equal 0 and solve for x. In order for the fraction to be 0, the numerators have to be 0. And when you solve, we get negative 1/2, 0 for one x-intercept, and 2, 0 for the other x-intercept. I just solved in my head. Because we didn't have enough room there. So we have that point there, and that point. Okay, so now let's find the horizontal asymptote. And this says plural, but obviously there's only going to be one in these problems. So in order to do this, we have to divide the numerator by the denominator in the unfactored form, and we get the following. And what that means, and let me move this down a little bit. I'm going to move this over. So we're now converting the form of that expression to 2 plus negative 7x plus 4 all over x squared plus 2x minus 3. So the horizontal equation is y is equal to 2, or the equation of the horizontal asymptote. And let's see, let's do a sign chart. So we have 1 and negative 3 and 2. So you want to get the x-intercepts and the vertical asymptotes on our sign chart. And again, the spacing may not be precise. That really doesn't matter. You don't have to sit there and worry about the spacing being completely correct. Okay, let's test this region here with this function. We've got it written down there. It's better to use factored form. So let's try negative 4. If we plug in negative 4, we get negative 7 times negative 6 over negative 1 times negative 5. And that's going to be 42 over 5. So 42 over 5 is 8.4. So we plug in negative 4, 1, 2, 3, 4, and we got 1, 2, 3, 4, 5, 6, 7, 8.4. So we've got that point there. And so that part of the graph is positive. Now let's try plugging in negative 1. that gives us -1 times -3 over 2 times -2, and we get 3 over -4, so -3/4. So that's going to be about there. Actually, that should be below the x-axis. So we get a negative number. Let's try plugging in 0 now. If we plug in 0, well, we already did that. We got 2/3. So our y values are going to be positive at that part. Let's try plugging in 1.5. That's this region here. And we get 4 times -1/2 over 4.5 times +1/2. So we get -2 over 9/4, and that gives us -8/9. So that's going to be a negative region. I can plot that point. That'd be about there. Now let's plug in 3, the final region to test. So we're testing this region up here with x equals 3. So we get 7 times 1 over 6 times 2, which is 7 over 12. So we plugged in 3, we got +7 over 12. And we also need to draw our horizontal asymptote at y equals 2. That'll help us. We can see that the graph looks like it's approaching that asymptote there, but we're not allowed to go quite that far to the right though. Okay, and let's try plugging in -2. We get -3 times -4 over 1 times -3. And that gives us -4. Connect the dots. Okay, and let's find some more points to the left. Let's try -5. So that gives us -10 times -7 over -2 times -6, 63 over 12. So 63 divided by 12 is 5.25. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5.25. And I'm just going to connect the dots there. Probably should find a few other points. Let's try -7. And we get -13 times -9 over -4 times -8. So you can use your calculator to help you. That's 117 divided by 32, which is 3.65. So that's about there. And we could plot some other points to be more accurate, but that's probably good enough. So was that tedious? Yeah, it was pretty tedious, but We're just getting the main idea of how to graph these curves. Now notice that the graph crossed the horizontal asymptote. That's fine. But a graph can never cross a vertical asymptote. Okay, so if you got those right, good job. And again, you can rectangle if you want. We forgot to write the equation of the horizontal asymptote there. We found the y-intercepts, the x-intercept, and so on and so forth. Okay, so now we're moving on to problems where the degree of the numerator is greater than the degree of the denominator. And in this case, we're going to have oblique asymptotes, asymptotes that are actually slanted or diagonal. So the first thing we need to do is factor, because we may have some holes that we have to consider. The numerator is the difference of two squares, even though this is not a square, it's a fourth power. But you can consider this to be x squared squared minus 4 squared. So that would look like this down in green. We have x squared squared minus 4 squared. So it's the difference of two squares. And we're going to factor by grouping. So I'm going to factor x squared out of the first two terms in the denominator. I'm going to factor out -4 from the third and fourth terms in the denominator. And then we can factor this expression here, because that's the difference of two squares also. So we're factoring the difference of two squares twice. So then we have x minus 2 times x plus 2 times x squared plus 4. And I'm going to factor out x plus 3 of these two terms, the green and the blue terms. They both have an x plus 3 factor. So I'm going to factor that out, and then we're left with x squared minus 4. But this purple factor in the denominator is the same factor we had in the numerator. But just so we can see where the holes occur, I'm going to factor or do one more step here. So I'm going to factor the difference of two squares in the denominator. So that becomes x minus 2 times x plus 2. And we can see that we have a hole at 2 and a hole at -2, because those factors cancel out. So before I forget, let's write the x values where those holes occur. So that one came from there, the other one came from there. And we can see that there's going to be a vertical asymptote at x equals -3. And in order to find the oblique asymptote, we're going to use the blue and yellow parts that are left over after we cancel out. So we're going to come up with a new function that we're going to call g of x. And that's going to be x to the second power plus 4 over x plus 3. And I'm just coloring these so you can see easily where they came from. And the reason we're using this reduced form is it's just easier to do the math, because the green and purple factors, they cancel out, so they don't really affect anything other than putting some holes on the graph. Okay, so now to find the oblique asymptote equation, we're going to divide the numerator of our reduced expression by the denominator. Looks like we're going to get x minus 3, and our remainder is 13, so we can rewrite that reduced form of the expression as x minus 3. Maybe I'll give that a special color so we know where that came from. X minus 3 plus 13 over x plus 3. Okay, so now changing the expression to this form tells us some useful information. As x becomes very big positive numbers or very big negative numbers, this fraction approaches 0 and it just becomes negligible. So as x gets bigger and bigger and bigger, this just, we don't really even need to consider that expression, because it kind of disappears. It gets so close to 0 that we just consider it to be gone. So this expression is left over, and so as x gets really big, the graph becomes more and more like the graph x minus 3, to the point where it gets so close we can't even differentiate. So what that means is we have an oblique asymptote at x minus 3, and oblique just means a slanted or diagonal line, because x minus 3 is an expression that gives us a linear graph. So that is the equation of the oblique asymptote. If we plug in 0 to x up here, we can see pretty clearly that 4/3 is going to be the y-intercept. And the blue factor there does not really give us any x-intercepts. The green and purple, again, those are not x-intercepts, those are just holes. That's something completely different. So if we use that blue factor to try to find some x-intercepts, because remember, in order to make y 0, because if you're going to try to find x-intercepts, you have to make y equal to 0 and then solve for x. In order to make y 0, we need to make the numerator of the fraction 0. We can't do that with the green and purple factors because they represent holes. They cancel out. So the blue factor is the only hope that we have. But if we try to set the blue factor equal to 0 so that we can find the x values that would make it 0, we come up with imaginary solutions. So imaginary numbers cannot be x-intercepts. So we can just say there's no x-intercepts. Okay, so now we're going to do a sign chart. We have a vertical asymptote at x equals -3, and we have no x-intercepts. So we're pretty much ready to go here. Now notice on this graph that every square represents 2 units, so be aware that sometimes that can happen. So we have a vertical asymptote at x equals -3, so that's going to be right here. Again, every square represents 2 units just on this particular graph. So now we have this this red oblique asymptote. So that's going to be it's going to be a line like we mentioned, and this equation is in slope-intercept form. So remember, y equals mx plus b. I'm going to write that in red. I'll write it in green. So y equals mx plus b. B is -3, that's the y-intercept, and m is 1, that's the slope. So the y-intercept is -3, that would be down here, and the slope is 1. So that means we go up 1 and over 1. Or we can go up 3 and over 3, however you want to do it. I'm going to do it that way. So up 3 over 3, up 3 over 3, up 3 over 3. It's kind of an awkward way to do it, but however you want to do it to graph this asymptote. Again, this is a oblique asymptote. So there you go. The graph approaches that line at some point. So now this graph, the y-intercept, it's 0, 4/3. So that would be roughly there. And let's do a sign chart. So let's say that x is 0. We're going to check this region over here. If x is 0, we get a positive number. We already found that. So the y values are going to be positive on that part of the graph. And let's try plugging in -4 to test this region over here. So let's plug in -4. I guess we can, it's probably be best to use the reduced form. Again, sometimes we can use the reduced form to help us. -4 is not where one of the holes occurs, so we can do that. So -4 plugged in, we get 16 plus 4 is 20 over -4 plus 3, so that'd be a negative number. So that tells us where our graph is above and below the x-axis. So now we have to plug in some points. And I know this is kind of tedious, but we just have to do it. The good news is that we can use our reduced form. We can plug it in here, or we can plug our x values in there. So let's plug in 2. So if you plug in 2, we get 8 over 5. So that's going to be about there. Let's plug in 4. Then we get 20 over 7. And 20 over 7 is 2.85. So that'd be about there. And let's try plugging in -2. So if you plug in -2, we get 8. We get 8 exactly. So 1, 2, 3, 4, 5, 6, 7, 8. And at this point you can connect the dots. So we just needed a few more points there just to kind of get a feel for where the graph is. So now we need to plug in let's try -4. So plug in -4 and we get -20. So that's going to be down there. Now let's try plugging in -6. If we do that, we get 40 over -3. So 40 divided by 3, and we get -13.3. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Approximately there. And we can probably connect the dots at that point. We have a good enough feel for where the graph is going to be. Okay, so there you go. But there's one more thing that we need to consider. And notice that the graph follows this asymptote, this oblique asymptote, the slanted line, as we go to the right and to the left in this case. Sometimes the graph will only follow as we go to the right, but not to the left, or to the left and not to the right. But in this case, the graph follows the asymptote in both directions. But the one thing that we haven't done yet is consider these holes. We have a hole when x is equal to 2. So what that means is we need to go and erase this point here and rewrite it as a hole. It has to be a hole, because that's where x is equal to 2. So we'll replace that with a little open circle there. It's kind of hard to see, but and then x equals -2, we also have a hole. So we're going to count out -2. And so we see that this yellow point there, that's going to be a hole also. So I'm going to erase that and draw a little circle there. So now we have everything that we need on the graph. And we can rectangle some of this information just to show that we found that. Okay, so let's try one more of these problems before you try one on your own. We need to factor the numerator because we don't want to confuse a hole for a vertical asymptote or vice versa. And so the vertical asymptote equation is going to be x is equal to +3 because we don't have any factors that are canceling out. And to find the oblique asymptote, we have to take the original expression and divide by, or take the numerator of the original expression, divide by the denominator of the original expression. We get a new form of our function, which is -x minus 2 minus 4 over x minus 3, and the oblique asymptote equation is y is equal to -x minus 2. Because as x gets really big, this fraction becomes negligible. It approaches 0, which means that the graph is going to turn into -x minus 2 for all intents and purposes. Now if we let x equal 0, we have negative 2/3. So 0 comma negative 2/3 is the y-intercept. It'll be about there. And we can see what the x-intercepts are going to be from the blue factors up there. I'm not going to rewrite them because that would take a while. So 2 and negative 1. And that's because to find the x-intercept, you let y be 0. So this expression has to be 0, but in order for a fraction to be 0, the numerator has to be 0. So x has to be 2 or negative 1. So let's plot those points. And let's graph the vertical asymptote. X equals 3. And the oblique asymptote, negative x minus 2. So the slope is 1. Or excuse me, the slope is negative 1, and the y-intercept is negative 2. So we have two asymptotes. And now we can do a sign chart. So we have 3 and 2 and negative 1. And let's plug in negative 2. We can plug it into this expression here. And we get 4/5. So let's plug in negative 2 for this region up here, and we'll plug it into the factored form of the expression, and we get the following. So that's going to be positive 4/5. So the y values are positive in that region. And we can see that our graph is going to look something like this. Let's try plugging in 0, and we get negative 2/3, and we already found that number, so that's negative. Let's try plugging in 2.5, and we get a positive, so that makes sense. And if we plug in 4, we get the following. Negative 10. So 1, 2, 3, 4, all the way down to 10. Let's try plugging in 5. Then we get 3 times 6, negative 3 times 6 over 2, and that would be negative 9. So So we plug in 5, we get -9. And at this point we can see what the graph is going to look like. Let's plot one more point. Let's plug in 6. Then we get -4 times 7 over 3. So -28 over 3. That's -9.3. One, two, three, 4, 5, 6, 7, 8, 9. So that gives us one more reference point. There you go. So, and I forgot to show the sign here. That's going to be negative y values. So notice that there's no holes on that graph because we didn't have any factors that canceled out up here. So I want you to get a picture of these problems. These are going to help you do number 7 and number 8. Okay, so try number 7, and when you come back, we'll do it together. Okay, we're back. So let's factor the numerator. We have the difference of 2 squares. And we can factor out x squared in the first 2 terms of the denominator, and we can factor out 9 of the first 2 terms of the denominator. And now you can see we have a common factor in the denominator, which is x minus 2. So I'm going to factor that out. And then we can factor x squared minus 9. That's also the difference of 2 squares. But we still have to factor the x squared minus 9 in the denominator. So we have x plus 3 times x minus 3 times x squared plus 9. And in the denominator we have x minus 2 times x minus 3 times x plus 3. So these green factors cancel out, which means we have holes at x equals 3 and x equals -3. We have a vertical asymptote at x equals 2. And we can write a simplified form of the function, which I'll call g of x. The reason I call it g of x instead of f of x is because it's not the same. The holes don't exist with this function, so it's not technically the same function. But we're going to use that function to do a lot of analysis. We're going to find the oblique asymptote by dividing the numerator by the denominator. And so we have x squared minus 2x. We have 2x plus 9. Then we add 2. And we get 2x minus 4. So the reduced form of the fraction can be written as x plus 2 plus 13 over x minus 2. And as x becomes really big, this fraction becomes negligible. It approaches 0, which means that this is the equation of the oblique asymptote. So let's go ahead and graph that. The y-intercept is 2 and the slope is 1. And we have an asymptote at x equals 2. And if we let x equal 0, we have negative 81 over 18. Which is negative 9 over 2. So the y-intercept is 0, negative 4.5. And we can see the x-intercept. That's one note throwing us around. Well, actually, there is no x-intercept because that yellow factor doesn't produce an x-intercept. If we want to make the numerator 0, you'd see x would have to be plus or minus 3i. That's an imaginary number. So now we can do a sign chart. We only really have one value to worry about, the vertical asymptote. Plug in 0 and you get a negative number. Plug in 3 and you get a positive number. So our graph should be above the x-axis to the right of x equals 2. And let's see. Let's plug in some values. Let's plug in 3 to the reduced form of the equation. Actually, I guess we can plug it in here. And we get 13 plus 5 is 18. So that's going to be off the chart. Let's plug in 4. Then we get 6.5 plus 6 is 12.5. So 1, 2, 3, 4. 12.5 would be about there. And let's plug in 6, and we get 45 divided by 4, which is 11.5. So that's going to be about there. Let's plug in 5. So we get 34 divided by 3. That's going to be 11.3. So that's about here. And we can connect the dots. And so now let's plug in 0. Actually, we already have 0. 0, negative 4 and 1/2 is there. Let's plug in 1. And we get negative 13 plus 3 is negative 10. That's off the chart though. Let's plug in negative 1. And we get 10 divided by negative 3, which is negative 3 and 1/3. It should be about there. Now let's plug in negative 2. That's going to give us 13 divided by negative 4, which is negative 3.25. So that's about there. So our graph is going to look something like that. Let's plug in negative 3. Then we get 18 divided by negative 5, which is negative 3.6. And we can just keep going on and on and on, but the graph is going to look something like that. as long as you understand the main idea. The graph doesn't have to be perfect. Okay, but now we have holes at x equals 3 and negative 3. So we have to make sure that those holes are there. Negative 3, that's going to be about there. Negative 3. And positive 3. So let's go out 1, 2, 3. So there's going to be another hole, but it's not really on a visible part of the graph, so we don't have to worry about that. Okay, so go ahead and try number 8, and when you come back, we'll do it together. Okay, we're back. So let's factor the numerator and denominator so we can see what the x-intercepts are and the vertical asymptote. And it might be useful to factor out a negative 1. You don't really have to do that, but you can do that in the denominator if you'd like. And this gives us some useful information. We know that there's vertical asymptote at x equals negative 1. So we got that from there. And if we let x equal 0, we can tell just using this expression here, we get 6. And so 0, 6 is the y-intercept. And we can see the x-intercepts are 2 and negative 3. And we can see that just by looking, because we want the numerator to be 0 in order for this expression to be 0, which would make the corresponding y values 0. So we've got our basic information, but we also need to find our oblique asymptote if we have one. So we're going to use long division, as we did in the previous problems. And so the new form of our function is negative x minus 6 over negative x minus 1. Now, we can simplify that. We can use the negative 1 rule as we did up here, pull out a negative 1, and then we have two negatives, that's a double negative, so we have negative x plus 6 over x plus 1. And as x approaches infinity, as x values become very big, this fraction approaches 0 and becomes negligible. So the graph approaches this line, negative x. So let's graph that asymptote line, negative x. The slope is negative 1, and the y-intercept is 0. We also have a vertical asymptote at x equals negative 1, and we have x-intercepts at 2 and negative 3, and we have a y-intercept at 0, 6. So that's a lot of good information to help us find the values that we're looking for. So let's mark the asymptote on our sign chart and the x-intercepts. Again, these numbers don't have to be spaced exactly the way they should be. That's not really the point. Okay, so now let's figure out the signs. We can use the factored form of the function. Plug in negative 4 and we get a negative times a negative is a positive, and the bottom we get a negative times a negative is a positive. So the graph is going to be above the x-axis there. Let's plug in -2. A negative times a positive is a negative, and a negative times a negative is a positive, so negative divided by a positive is a negative. Now let's plug in 0. We can do that up here, but we actually already did that. We got +6, so that part of the graph is above the x-axis. And now let's plug in 3. Plug in 3 up here, we get a positive times a positive is a positive, and in the bottom we get a negative, so that part of the graph will be below the x-axis. So now we have pretty much everything that we need. We can find a few more points if we want to be a little more accurate. So let's try plugging in 1, 2, 3, 4. And we get 2 times 7 over -5, so that's 14 over -5, which is -2 4/5. So 1, 2, 3, 4, 1, 2 4/5. And we can see at this point what the graph is going to do. We could be a little bit more accurate by plotting more points, but that would take a long time, and it's not really that important. We just want to get a feel for what the graph looks like. Let's try plugging in -5. Then we get -7 times -2 divided by +4. So that would be 14 divided by 4 is 3.5. So let's plot that. 1, 2, 3, 4, 5, 1, 2, 3.5. Just gives us kind of a guide. Now let's try plugging in -1. So we have -3 times 2. Actually, sorry, I meant to plug in -2. -1 is where the asymptote is. So they get -4 times 1 over 1. Then we get -4. So if you plug in -2, we get 1, 2, 3, -4. So now we're ready to connect the dots. And so there you go. If you got those answers, good job. And we forgot to write the equation of the asymptote. That's y is equal to -x. That's an oblique asymptote. So if you got that one right, excellent. So we did problems where the asymptote was horizontal, but it was not on the x-axis, as opposed to the previous class where all the horizontal asymptotes were on the actual x-axis. Then we did problems just now where we had an asymptote that was not horizontal at all or vertical. It was oblique, meaning slanted or diagonal. But now we're going to talk about curved asymptotes. Asymptotes that are actually curved, an invisible line, not really a line, but an invisible curve that the graph approaches. These graphs are somewhat difficult to draw, so you don't have to draw them, but we're going to find some information about them, and I am going to show you a picture of the graph on a graphing calculator. So what we're going to do to analyze this graph is find the equation of the asymptote curve, the x and y intercepts, the vertical asymptote, and any holes that exist. So just like we did in the previous problem. So I'm factoring a GCF in the numerator and the denominator. And we're going to factor one more time. We have 4 x's in the numerator and 1 x in the denominator. And I'm going to factor that quadratic. So now you see that we have a hole at x equals -1. Because that factor canceled out. We also have a hole at 0 because if you plug in 0, you get 0 in the numerator or the denominator. And we have a vertical asymptote at x equals -3. That green factor tells us that. And the y-intercept, well, there's no y-intercept because there's a hole at 0, 0. If you plug in 0 for x, then you get 0 for y. That's what these factors up here tell us. The problem is those x's there, they cancel out. So if there's a hole where the intercept should be, then that means the intercept doesn't exist. And the same thing is true for the x-intercept. If you plug in 0 to x, you get 0 for y. But again, we know that there's a hole there. And I forgot to write that. X equals 0. Okay, so now let's find the curved asymptote. To do that, we can use the reduced form. When we cancel out all those similar factors, we get a new function, which I'll call g of x, which is x cubed. I got that from these factors here. Maybe I'll use a different color. And the x plus 3 factor is still there. I got that from there. And so we can use long division, again using the reduced form of the fraction. And we have looks like -27 for the remainder. So we can rewrite g of x, the reduced form of the function, as x squared minus 3x plus 9. And we need to add our fraction at the end there. So minus the remainder divided by the divisor. So here's where this is different. Notice as x becomes very large, this fraction becomes negligible. So it approaches 0, and the graph gets closer and closer to whatever this would be. And so you can see that our asymptote curve is not a line. It's not a horizontal, vertical, or slanted line. It's actually a curve. It's a parabola. That's a parabola. So to demonstrate that, I'm going to use a graphing calculator that you can find on the App Store for your iPhone. it's free. And as we zoom out, you're going to see that the graph is going to look more and more like this parabola. Y equals x squared minus 3x plus 9. And now we'll zoom in and go back to the part of the graph that's near the origin, and then we see the features of the graph. So again, that's why this is a curved asymptote. Okay, so let's try one more of these. We're going to factor by grouping. I'm going to factor out x squared from the first two terms. And I can just factor out 1 on the other term so we can see what's going on here. Then I'm going to factor out x minus 2 from the two terms in the numerator. So I wrote the expression in factored form, and now we can see the vertical asymptote is -2, so I got that from there. And by the way, we can plug in 0 for x, and we get -1, so the y-intercept is 0, -1. And I forgot to rectangle these. I forgot to write the equation of the asymptote curve. Now we have an x-intercept if x is equal to 2. If x is equal to 2, then we have an x-intercept. That makes the fraction 0. So I got that from there. And the other factor doesn't really lead to anything because there's no number you can plug in for x that would make this blue factor 0 unless you want to use imaginary numbers. And imaginary numbers cannot be x-intercepts. Okay, so now we need to focus on the asymptote curve. So we'll take the original numerator there and divide by the denominator. Okay, so now our reduced form of the function, and we can call it f of x because there were no holes that we had to worry about. So we have x squared minus 4x plus 9 minus 20 over x plus 2. So as this expression approaches infinity, or as the x value approaches infinity, positive or negative infinity, this fraction approaches 0. In other words, as x gets really, really big, a big positive number, or a really, really big negative number, this fraction approaches 0 and becomes negligible. So the graph approaches this curve, and for all intents and purposes, when x is really big, the graph gets so close to this curve that it actually looks like the curve. So that means that that expression there is the invisible curve that the graph approaches as x becomes a very big positive number or a very big negative number. So sometimes your asymptotes can be horizontal and on the x-axis, as in the previous class. Sometimes the the asymptote can be a horizontal line that's not on the x-axis, as the first problems that we did today. Sometimes the asymptote can be a line that is slanted. We did those problems today also, but here you can see that an asymptote can actually be a curve. So now it's time for you to try. I want you to take a picture of these problems here. And by the way, we didn't have any holes on number 10. We had two holes on number 9. Go ahead and try number 11. When you come back, we'll do it together. Okay, we're back. We don't have time to do this problem together, so I'm just going to show you the answer. So if you got those expressions and numbers, good job. Go ahead and try number 12, and when you come back, we'll do it together. Alright, we're back. So we don't have time to do the problem together, but here's the answer. If you got those expressions and numbers, good job. So that was the class today. If you'd like to take screenshots of the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3 and number 4 and number 5, number 6, and number 7, but don't go before you get the homework assignment. Let's take a look at the homework. Here's screenshot number 1 of the homework. And number 2. And number 3. But don't go before you get the answers to the homework. Here's the answers. Make sure that you do the homework properly. And here's the last screenshot of the answers for the homework. So get that homework done completely, correctly, and neatly, and keep it in order. And I'll look forward to seeing you in the next class.